All right, let's look at your sample test for 4.851 to 54. So first off, if we are trying to approximate the area under the curve for 1 plus x squared on the interval to 7 and using left-hand endpoints, then we're going to first off find our change in x. So we're going to say b minus a, stopping point minus starting point, divided by n, the number of rectangles. And so that tells us each one is 1 unit wide. So let's start at our a value 2. And we'll go 1 unit to 3, and then 3 to 4, 4 to 5, 5 to 6, and 6 to 7. Now, if they asked me to find right-hand endpoints, I would have been using the 3, 4, 5, 6, and 7. But since they asked me to find left-hand endpoints, then I'm going to use 2, 3, 4, 5, and 6. So out in front here, we're going to have our change in x, which is just 1. And then f of 2 literally means plug 2 into this function. So 2 squared is 4 plus 1 is 5. F of 3 means plug 3 into the function. So 1 plus 3 squared would be 1 plus 9 or 10, 1 plus 16, 1 plus 25, 1 plus 36. So that gives us our approximation. Then they ask us to use the same subinterval and the same equation, and they ask us to use midpoint rule. So again, our change in x is just going to be 1, and we're going to have those same intervals, but this time we want the midpoint of those intervals. So that would be 2.5, 3.5, 4.5, 5.5, and 6.5. So when we do our midpoint, we're going to have our change in x out in front. And then f of 2.5 just means plug 2.5 in for x. So 2.5 squared is going to be 6.25 plus 1 is going to be 7.25. Take 3.5 and plug it in. 3.5 squared is 12.25 plus 1 is 13.25. And then we will plug in 4.5 and 5.5 and 6.5. And so 116.25 would be our midpoint approximation. All right, then for our next section, we are using the fundamental theorem of calculus, so we don't have to work it out long way. We can just use our shortcuts. So one of our properties says that if your a and b value are the same, that your answer is going to be 0, because if you start and stop at the same place, nothing is getting enclosed in that area. The area would be 0. All right, then for the next one, we have a piecewise defined function. And so for a piecewise from 0 to 1, we're going to use x cubed, and from 1 to 3, we're going to use x squared. And it's literally like working 2 problems in one. I'm going to go through and do the antiderivative for the first one and plug in 1 and 0 and subtract. And I'm going to go through and do the antiderivative for the second one and plug in 3 and 1 and subtract. So you can see here I plugged in the 1 to get 1/4 minus plugged in 0, plus over here for my second problem I plugged in 3 to get 27 over 3 or 9, and then plugged in 1 to get 1/3. So when I combine all of that, I will have my area. All right, for the next one, there's literally a statement on the test that says don't make this one harder than it is, because it looks confusing, but it's very straightforward. So remember we had that property that said if you find the area under the curve from 0 to 4 and add to that the area from 4 to 6, that would be the same as the area from 0 to 6. They're going to give you 2 of those 3 pieces. So they told me that 0 to 4 was -5, and they told me that 0 to 6 was 3. So all I have to do is just say -5 plus 1 is equal to 3, or add 5 to both sides. All right, then for number 6, we're going to do normal antiderivative and then plug in values. So antiderivative of sine is negative cosine. Derivative of cosine is negative sine. Antiderivative of sine is negative cosine. And we still have that 4 out in front. We need to plug in our pi over 2 and 0. So we'll plug in pi over 2 and then subtract plugging in 0. So cosine at pi over 2 is 0. And cosine at 0 is 1. So we'll plug those values in, and then we can simplify. So for number 7, we have an absolute value, and an absolute value is always a piecewise defined function. So first off, I need to figure out where this thing is positive and negative. So I'm going to take 3x minus 2 and set it equal to 0 and solve, and I get 2/3. So I know that I have a root here. So I'm going to pick a test point like 0 and plug it in. So if I plug that in, I get -2. So it's negative here across a single root. The sign changes to positive. So with the absolute value, anywhere what's inside the absolute value is negative, I'm going to use the opposite of my equation. So the opposite of 3x minus 2. And then anywhere it's positive, I'm going to use the exact equation, the 3x minus 2. So notice that we're starting at -1. So from -1 to 2/3, I'm going to use the opposite. And then from 2/3 to where I stop at 2, I'm going to use the exact function that I started with. All right, so then I'm just going to do 2 antiderivatives. It's like 2 problems in one. So I'm going to do 2 antiderivatives. And then again, as before, I'm going to plug in 2/3 minus plug in -1. And then I'm going to plug in 2 minus plug in 2/3. All right, then for our next one, we're using another property that says if you have A and B and you swap those two values, what does that do to your function? All it does is just changes the value to the opposite. All right, then for number 9, we have normal integration. So first off, we're going to do the antiderivative. So add 1 to 2, and we get 3 divided by that same number. Add 1 to x, and we get 2 divided by that same number. This is 2x to the 0, so add 1 to that, and that would be 2x to the 1 divided by that same number 1. All right, so now I can go through and I can plug in 5. So we plugged in 5 right here, minus plug in -1 right here. And then we can simplify and get our answer. All right, for the next one, if I try to do the antiderivative, first off, I need to think about the domain. What is the domain of this function? Well, your domain is all real numbers unless you get 0 in the denominator or negative under an even indexed radical. So for this one, our denominator cannot be equal to 0. That function does not exist at 0. We cannot integrate it where it doesn't exist. So this one would be does not exist. Now, if instead it had said go from +2 to 4, there would be no problem with that because 0 would not be in that interval. All right, so you would be turning in your first page here and swapping, and then you'd be able to use your graphing calculator for all the rest of these. Let your calculator do the integration for you. I've already assessed that on the first part. I don't need to do it again on the second part. So average value of a function, we need to know that that's just normal integration times 1 over b minus a. So for us, our interval was 0 to 3. So we're going to say 3 minus 0. So 1/3 times the integration of 6x minus x squared. Now, I worked this out just so you would have an extra example by hand and so that you would also see working it out by hand, I get 6, but that's the exact same thing if I took this guy right here and I just typed it straight into my calculator. So you're on the calculator page, you can let your calculator do your definite integration for you. All right, so the second, number 12, we want to use the definition of the definite integral. That's our long way. And so here's our definition of the definite integral. You might remember that we had done like the limit of the summation was the same as the sigma. And then our function was our function. And then dx was similar to change in x. That was how we had gotten our definition. So first off, I need to find x sub I and I need to find change in x. So change in x is just b minus a over n. And x sub I is just a plus the change in x times I. So if I do b minus a, 2 minus 0 over, I don't know how many rectangles it is, so it's just going to be 2 over n. And then x sub I is going to be a, so a was 0. And then change in x was 2 over n times I. That would just give us 2i over n. So now let's replace x sub I with what we just got, 2i over n. And then let's replace the change in x with what we got, 2 over n. 2 over n is just a constant, so we can move it out in front and get it out of our way. So here it is. And then if it asks me to do f of 2i over n, that literally means put 2i over n in the place of x in the function. So I'm going to put 2i over n right here and 2i over n right here. So that would be 2 times 2i over n minus 2i over n squared. 2 times 2i over n minus 2i over n squared. All right, so now we can simplify that a little bit. So the way that we do that is 2 times 2i is going to give us 4 over n times I. And then here 2 squared is 4, I squared n squared. So 4 over n squared times I squared. If we have two things that are being subtracted, we can break that into two separate sigmas. So the 2 over n goes with both of them. So you can see the 2 over n with both of them. And then here, this 4 over n, again, is just 4 divided by a number of rectangles. So it can move out in front as a constant. And this 4 over n squared, the same. It can move out in front as a constant. So now all we have left is the summation of I and I squared, and we have formulas for those. So 2 times 4 is going to give me 8 over n squared, and then this is just the formula for the summation of I. And then 2 times 4 is 8, n times n squared is n cubed, and this is just the formula for the summation of I squared. Now, I want to put my numbers together and put my variables together. You can multiply in any order, like 2 times 3 is the same thing as 3 times 2. So I'm going to just put 8 over 2 and n times n plus 1 over n squared. And then same thing here, 8 over 6, and then I'm going to put the n's over each other. Now, this numerator right here, if I distributed, that would be n times n is n squared plus n. And this one, if I did n times n plus 1, that would be n squared plus n. And then if I FOILed it to this 2n plus 1, I would get this cubic. All right, so 8 over 2 is where this 4 is coming from. And then here, n squared over n squared. And then n over n squared minus 8 over 6 is giving me 4/3. And then here 2n cubed over n cubed, 3n squared over n cubed, and n over n cubed. All right, so let's reduce those down. So we know n squared over n squared is 1. N over n squared is 1 over n. 2n cubed over n cubed is just 2. 3n squared over n cubed is 3 over n. And then one of these n's would drop out to give me 1 over n squared. Now, when I'm taking the limit approaching infinity, remember that the limit of a constant is that constant. The limit of a constant is that constant. The limit of a number divided by a variable raised to a positive exponent is 0. So this is just going to give me 4, 1, 0, 4/3, 2, 0, 0. And then I'm able to combine those values to come up with my final answer of 4/3. Now let's go back and let's do it with the fundamental theorem of calculus with our shortcut. All right. So first off, I'm going to do the antiderivative here. So this is x to the 1. So it'd be x to the 2 over 2. And x to the second, add 1 to that. That'd be x to the 3 dividing by that same number. Then I'm going to go through. I could take cancel these 2's right here just to clean it up a little bit. So if I take 2 and plug it in, then I'm going to end up with 4 minus 2 cubed is 8/3. Minus, plug 0 in, I'm going to get 0 minus 0. So that would give me the same 4/3 long way as I got with the shortcut. All right, for 13, remember that if you take the derivative of an integral, they cancel each other out. They undo each other. And with the integral sign goes the dt. They're a pair. They always go together. But notice that this was in terms of x. So when I cancel this out, I have to replace that t with x because I was taking the derivative in terms of x, not in terms of t. All right, then for 14, they gave me the acceleration and they asked me to work back to the position function. So if we integrate acceleration, that takes us, acceleration is the second derivative, that takes us back to the first derivative, velocity. So we're going to do the antiderivative of acceleration and we'll get velocity. And notice they told me that if you plug 0 into the velocity equation, you'll get 3. So I'm going to plug 0 in for each of the t's, and I know the answer will be 3 when I do. So notice that just leaves me with c is equal to 3. So let's put 3 in the place of c, and now I have an exact definition for velocity. To get back to position, I need to integrate again. So I'm going to integrate one more time because the integration of velocity would be position. Velocity is the first derivative, so that takes me back to the original. So again, I'm going to do the antiderivative, and again, I have an arbitrary constant. Don't call it c because c was 3 and this might not be 3. So if I plug in 0, they tell me that d is -2, and so I can